All right, in our last class we talked about it. We mainly reviewed a two-dimensional model and how its surrounding flow field changes with the angle of attack. Today, we will continue with the content from last time to discuss the system characteristics related to the two-dimensional model. When discussing system characteristics, the first aerodynamic characteristic we focus on is the one most related to our flight, which is solving the problem of getting airborne. That is, the principle of lift generation. In fact, we have mentioned a bit about the principle of lift generation before. Let's review it again to recall the nature of it. Do you remember the first form of lift generation we talked about? It was the Magnus effect, right? A rotating sphere or a cylinder, during its rotation, causes the surrounding air to change its velocity. So if there is a forward motion speed while it is rotating. Do the students in the back have any questions? A rotating cylinder, if it has a forward motion speed, rotates counterclockwise. Now, if we talk about it, it rotates clockwise. In this case, on the upper surface, because the incoming flow from the left side is consistent with the direction of the rotational speed of the upper surface, it causes the airflow on the upper surface to accelerate, reducing the pressure, while on the lower surface, it decelerates. The pressure difference increases, creating a pressure differential between the top and bottom, right? This is lift, yeah, right? This is lift. At the same time, we say that a rotating cylinder can also be understood as bringing a rotational speed to the flow field, which we call circulation. When there is a horizontal speed combined with circulation, lift can be generated. This is known as the circulation theory. So, what about the turbulence caused by the pandemic? Although the pandemic turbulence is not a rotating cylinder, in terms of its physical effect, it actually brings a similar effect, excited to the flow field, causing it to rotate. This results in an increased speed and decreased pressure on the upper surface, and a decreased speed and increased pressure on the lower surface. This is due to the circulation caused by the unique shape of the pandemic. This airflow acts on the wing, generating lift. Alright, here some students might feel that the concept of circulation around an airfoil is somewhat abstract. So we will use a concrete experimental example to demonstrate this. In a fluid, due to relative motion, circulation is generated. When an airfoil moves through the fluid, it creates this kind of vortex flow. We refer to this as the starting vortex when the wing begins to move. This vortex refers to the circulation. This means that when an airfoil is in motion, it has circulation. But when it stops, this circulation will shed off. We believe you can observe a vortex from the cessation of motion. Amazing, isn't it? Here, we're not asking you to fully understand this theory, but rather to observe this phenomenon and recognize that circulation indeed exists, right? We see that the one behind is the starting vortex, and the one in front is the stopping vortex. Alright, and then, this is about explaining lift using circulation theory. At the same time, we also have another explanation, which is using the co-flow theory to explain lift, right? We can see that whether it's the flow around a cylinder or our asymmetric flow, before reaching the object, the airflow moves upwards, and after passing the object, what happens? It changes to a downward sinking flow. Therefore, since the change in flow direction inevitably involves the action of force, it indicates that the air is subjected to a downward force, which changes its flow direction. Consequently, where there is an action force, there is a reaction force. Since this force is exerted by the object on the air, the air naturally exerts a reaction force on the object. This reaction force is the lift. This is the explanation method of lift according to the momentum theory. The above is a relatively straightforward and simple explanation of the mechanism of lift generation. Currently, there are some explanations of lift that are not very accurate, so I will briefly provide some scientific clarification for everyone, just for general knowledge. Firstly, the most common inaccurate explanation is called the longer path same time theory. What does this refer to? It refers to the idea that for an airfoil, when the airflow splits at the leading edge into two streams, they will reach the trailing edge simultaneously. At this point, because the distance over the upper surface is longer, and the distance over the lower surface is shorter, the flow speed over the upper surface must be higher to reach the trailing edge at the same time, while the flow speed over the lower surface is lower. Then combining this with Bernoulli's principle, it results in lower pressure on the top and higher pressure on the bottom. There is such a statement, but this statement is actually incorrect. Why? We can prove it through experiments. He's often said, I lived in the rooms generally. Therefore, he said, last year this common explanation is actually wrong. The distribution doesn't cost, but it doesn't reach the end of the way at the same point in the air. Very useful, big on the screen outside. When horses turn by, who's the interactive part? Thank you, everyone. And now so the video around. That is, you know, your pop off. No, it's been impossible. Here, you can see speed up as it approaches here. You say that. What do we see here? The flow speed on the top is indeed faster than the flow speed on the bottom, but they do not reach the rear source simultaneously. So here it confirms for everyone that the first and most common popular science explanation is incorrect. Additionally, there is another explanation called the skipping stone hypothesis. What does this mean? When an airfoil flies through the air hits the underside of the airfoil due to the positive angle of attack and then bounces downward. Because of this bouncing effect, it gives the machine a force, which is what we refer to as lift. So according to this explanation, where does the lift come from? It is generated from the underside. However, as we mentioned earlier, looking at the pressure distribution, where does the lift primarily come from? That's right. Therefore, this explanation is actually incorrect as well. But there is a special circumstance where this explanation might make some sense. In what situation does this explanation have some validity? Mainly when approaching the edge of the atmosphere. Where the air is very thin, the generation of lift is more akin to this form of principle. However, our commercial airplanes cannot reach this altitude, so it's enough for everyone to just be aware of this explanation. This is the second skipping stone hypothesis. The third explanation is called the semi-Venturi hotel hypothesis. What does it mean? It suggests that, regarding the pandemic, if you can connect the front and back edges into a line, then by connecting these edges into a line, you can split the upper field into two parts. All right, let's observe the upper part. Well, in this upper part, you can see that it forms half of a spherical hotel, right? So this half of the spherical hotel has a narrow throat, right? This part is wide, this part is wide, and this part is narrow. In the narrow area, the flow speed is relatively high. So in this area, the pressure is low, thus creating a low pressure zone. However, this method actually has its issues. What are they? If you consider this shape as half, along with the streamline as half of a spherical hotel, then in reality, it suggests that this area, the downstream region, is actually an expansion flow card. What does this mean? It means that in an expansion flow field, the flow velocity will decrease. So what happens at the back? That in reality, it becomes a high pressure zone. However, for our actual terrain, when the flow passes over the shape to the back, this part has already turned into a free stream with atmospheric pressure by the time it reaches the downstream. Therefore, this method is incorrect. Furthermore, if we explain it in this way, for a flat plate under a -0 angle, based on the assumption of this hemispherical model, if I consider it this way, by splitting it along a line connecting the leading and trailing edges, then this would be a contraction flow, right? A healthy flow field should be accelerating, which means what? Acceleration and pressure reduction, so it should generate an upward lift. But in reality, this flat plate, under the side view angle, if it is a symmetrical force type, it actually generates a negative downward lift. So this situation is also incorrect. So above, we discussed two correct methods to understand lift. One is the circulation theory, and the other is the momentum theory. Additionally, there are three common incorrect relative solutions, and it's enough for us to roughly understand where these inaccuracies lie. Next, let's take a look at the specific process of lift generation. That is, how lift and drag change as the angle of attack increases. Here, we focus on the changes as the angle of attack increases. The relationship between the life coefficient and the life coefficient. Do you remember how we can derive the total lift from the physiological coefficient? Do you remember this formula? What kind of relationship do we connect using the lift coefficient? What two things can we connect using the lift coefficient? Okay, so that's the macroscopic relationship. What we're talking about is using the lift coefficient, and the most important thing is that we connect the lift characteristics of the small model with the full-size aircraft, right? This lift coefficient is the same. Now, let's observe how the lift coefficient changes as the angle of attack increases. Here, we are using the NAKA 2412, which has a camber of 2% and a relative thickness of 12%. All right, so the relationship of the lift coefficient change as the angle of attack increases is directly plotted here. From this graph, we hope that students will pay special attention to the following features. First, we can see that as the angle of attack increases, the lift coefficient increases in the first half, particularly when the angle of attack is within the range of small to medium angles. I've highlighted this with a blue line. What do we notice? It is a change that is close to a straight line, right? This kind of change, similar to a straight line, is what we call a linear change. Linear, as the name suggests, is in the form of a curve like x plus d. A special manifestation is a straight line. At this time, we call this straight line the lift line of the two-dimensional operation. On the lift line, we can first observe that this line corresponds to an edge with a lift coefficient of 0. What does it mean when the lift coefficient is 0? Lift is 0, right? So what is the effect when the lift is 0? We call it the zero lift angle of attack. When at this angle of attack, the wing will not generate lift. And what happens when the angle of attack is greater than this angle? Naturally, as the angle of attack increases, how should the lift angle of attack behave? It's a proportional relationship, right? So, in other words, as the influence increases, the lift coefficient, increases the further it moves away from zero influence. This proportional relationship is what we call the lift curve slope, which is essentially this lift curve. The slope of this line is represented by CL alpha. Within this small range of angles, our lift coefficient can specifically be expressed as the lift coefficient equals the lift curve slope, multiplied by the current angle of attack minus the zero lift angle of attack, we see it forming such an expression, right? This aligns with the basic definition of a straight line. All right, so here, I would like to ask everyone a question. When our airplane is flying normally, we see the airplane flying like this, right? It has a positive angle of attack, which generates upward lift, and the lift counteracts gravity, allowing it to fly like this. All right, so what happens when the airplane is flying upside down? What kind of state is it in? What should its angle of attack be? Why can an airplane fly upside down? What does it generate? What kind of state should inverted flight be in? Ultimately, the state we see might not be certain. A paper friend mentioned it during inverted flight. As for the airplane, it should actually be in a state with an angle of attack less than the zero lift angle, right? not just a negative zero angle, because typically with this kind of positively cambered airfoil, its zero lift angle is actually a negative value. So when it is flying upside down, its angle of attack will be less than the zero lift angle, leading to a negative lift coefficient. Now, a positive lift coefficient is upward, but a negative lift coefficient is downward for the airplane itself. This is in a direction perpendicular to the incoming flow and downward, right? At this point, it can precisely achieve a balance between lift and gravity when the airplane is upside down. This is a basic characteristic we derive from the lift curve at small to medium angles of attack. Then further, we look at what kind of phenomenon occurs as the angle of attack increases to a large angle. We say that from here, as the small angle of attack continues to increase, to a certain extent, it begins to exhibit a nonlinear characteristic. This, after it changes from a straight line to a curve, at a certain angle of attack, it reaches the maximum value of the lift coefficient. Then, as the angle of attack further increases, what happens to the lift coefficient? You can see that it doesn't increase, but rather decreases, right? At this point, as the angle of attack increases, the phenomenon where the lift coefficient doesn't increase, but instead decreases is crucial for pilot safety. This is known as the stall phenomenon. In English, it is represented by stall. Specifically, the point at which it stalls corresponds to when the lift coefficient, at its maximum, the corresponding angle of attack is what we call the stall angle of attack, represented by C. The corresponding maximum lift coefficient might be represented by CL max. This is the critical state at the very edge when the aircraft reaches a stall. Therefore, in English, this stall angle is also called the critical angle of attack. Critical refers to this critical state. We need to pay attention to a linguistic issue here. In Chinese, 休止 we call it stall, which seems to imply a loss of speed. But what is the essence of a stall for any aircraft? The essence of stalling for all airplanes is the same. The cause of a stall in any situation is the angle of attack exceeds the critical angle of attack. This phenomenon is related to the airplane's speed. It has absolutely nothing to do with it. Understanding this concept, which we mentioned for the first time today, will be reiterated throughout the entire first part of our Aerodynamics Fundamentals course. As pilots, we must have this fundamental understanding, which is what? There is only one possibility for a stall to occur, which is when the airplane's angle of attack exceeds its critical angle of attack. Alright, this is what we observe from a two-dimensional curve, the characteristic of lift, changing with the angle of attack. Here, I hope students understand our lift curve, slope, the slope of the lift curve, the effect of stalling, and the physiological coefficient corresponding to stalling, or the maximum physiological coefficient. Now, let's look at this exercise, which is a question from our reference book. Here, we first assume that we understand this two-dimensional routine physiological characteristic as the physiological characteristic of boxing. Alright, there are a series of questions here that we hope our students can answer. First, let's look at the basic situation. So, an airplane, right? This airplane is a 60-ton airplane, correct? 60,000 kilograms, which is 60 tons. And then, in order to generate enough lift to keep the airplane hovering in the air, we need to produce a lift equal to the gravity. So, from there, to convert mass to gravity, it should be multiplied by 9.8. Then, this airplane has a wing area of 105 square meters. We take the standard atmospheric condition for air density, which is 1.225 kilograms per cubic meter. Alright, so the first question is, how many newtons of lift are needed to keep the airplane in level flight? We all should know this, so we won't go into detail. The second question is for everyone to calculate the airspeed in knots when the lift coefficient of the airplane at this point is 0.384. What airspeed is needed to maintain hovering? I'll give you 2 to 3 minutes. Let's give everyone an additional minute, making it 3 minutes. This is a very important fundamental calculation in our entire study of flight principles. We need everyone to master the calculation of the relevant lift formula. Additionally, there are some basic conversion relationships. Go. We hope everyone knows that metric units should be used with metric units, and imperial units should be used with imperial units. After we finish the calculations, how do we convert between metric and imperial units? There's 1 minute left. I see not many students have submitted. Should we extend the time? Oh, yes. Okay, finish typing first. All right, extend by 1 more minute. If you've forgotten the lift calculation relationship, let me remind you that lift should equal what? 1 or 2 times the air density, times velocity squared, times the actual area, times the lift coefficient. All right, the final minute. Time's up. Everyone has a lot of ideas. All right, let's just pick someone to explain how they did it. Are you here? Which one did you choose? I chose A. You chose A, right? You chose A. So what did you do? Let's switch to another person. Are you here? Is the red one here? Is it 0? Okay, let's switch to another one.
Are you here? What did you choose? Oh, I haven't finished yet, but I know that it seems okay not to finish. You said you know which ones are okay. Let me say something. First, the formula is 1 or 2 of that meat, in terms of 4LV, and then it's Vn. It equals this, the lift and gravity balance, right? So it equals the gravity of the plane, including listing an equation, solving for that speed, and after solving for this speed, the unit should be per second, then it should be converted to per hour.
What should be the conversion relationship between your two results?
Still not quite liking it. Now thinking about it, the conversion is 1 knot equals 0.514 meters per second per hour, that is. But,
come sit down. Actually, I'm really curious why many students, more than half, didn't get it right, huh? So let's take a look at the process. Actually, the thought process the student mentioned is correct. There's nothing wrong with it. It's just that they're not very familiar with using the calculator. In our final exam, we will have this kind of calculator, and this is all considered very basic calculation content, which is directly related to the performance of the aircraft. When the aircraft is in level flight, there should be a relationship where lift equals weight, right? In this case, we directly bring in the lift formula to equal gravity, right? Well, at this point, we can directly transform it, can't we? Keep the velocity on one side of the equation and move everything else to the other side. The 1, 2 becomes 2, right? 2 times g, then divide by u, divide by the area S, and then divide by the lift coefficient, right? Then take the square root. Then, the next step is to substitute the values, right? Note that we are using gravity here, so we should use mass times acceleration. In this case, using the 2 in front, multiply by the mass, which is 60 tons, or 60,000 kilom, then multiply by 9.8. Then, divide by the air density of 1.25. Then the lift coefficient is 0.384, and the wing area is 105 square meters. Finally, we get, the speed of the aircraft. 154.38 meters per second, and then blow the clouds. Then shouldn't we convert it from metric to imperial units? During our flight process, actually, when we fly domestically, the wind speed is usually reported in meters per second, right? But in fact, in the manuals, we often refer to imperial units. So how can we quickly perform the conversion? Actually, we should just multiply this number by 2. This way, we can get a very accurate and approximate value. 154 multiplied by 2 should be about 308, which corresponds to roughly 300 knots. Why is that? To convert meters per second to kilometers per hour, which is often used in exams, you should directly multiply by 3.6, right? And then, the conversion relationship between kilometers and nautical miles? Yes, it should be. 1 nautical mile equals 1.852 kilometers. So when handling this 1.852, notice here it's 3.6 and here it's 1.85, which is close to 1.8, exactly double, right? So we directly multiply the number of meters per second by 2, which basically corresponds to knots. This is a very important conversion relationship for us. All right, this way we get that its final airspeed should be 300 knots. Understand, if any students made a mistake, I hope you go back after class and review this conversion relationship. This is the most basic content we need to master. All right. Furthermore, using a similar method, we can calculate all the corresponding values for every point in the entire experience. Next, let's answer this series of questions from the book. The third question is, what is the minimum airspeed allowed for this aircraft during level flight? Note it asks what the minimum airspeed is during level flight. Let's look at this. Look at this curve, classmates. Let's get another volunteer. Are you here? Yes. Here, come on. What is the minimum wind speed that can be achieved? What? 150 meters per second, is that right? Money, money, money. Sit down, okay? Note that the unit we use here for our aircraft speed in imperial units is knots, right? We use nautical units, so when the aircraft reaches the maximum lift coefficient, The corresponding speed is the minimum airspeed the aircraft can fly. Therefore, at this point, it should correspond to 150 knots. If the speed decreases slightly more, and we still want the aircraft to pull a larger angle of attack, well, what happens to the aircraft? It stalls, right? Okay, the next question. Let me see. So, the maximum lift coefficient. What is the maximum lift coefficient we can use during level flight? We just mentioned it earlier, right? For this particular aircraft, it corresponds to 1.532, or if we want to be more precise, it is the stall lift coefficient, or the maximum lift coefficient. Alright, so this is the answer for C and D. Now, for question E, if an aircraft wants to maintain level flight, then okay. Is there an angle of attack that corresponds to a specific speed and wind speed? Is there a one-to-one relationship between airspeed and angle of attack? Here, I'll explain again for everyone. Yeah. If you're worried that I'm leaving something out, is there truly a one-to-one relationship between true airspeed and the aircraft's angle of attack at a certain altitude? Isn't it? Yes, it is. Right? Because the lift equals the weight. And the lift is determined, correct? At a certain altitude, the density is determined. And then, what does an angle of attack correspond to? A lift coefficient, right? Once the lift coefficient is determined, and the area doesn't change, doesn't that mean the speed is determined? There's no problem with that, right? So, when the altitude is fixed, our airspeed and angle of attack should have a one-to-one relationship. It's precisely because of this one-to-one relationship that we can map each point on this graph to a common reference. Isn't that correct? All right, then the next question. If the airspeed of the aircraft increases, and at the same time we want to maintain level flight, what should happen to the aircraft's angle of attack? What should happen to our angle of attack? It should decrease, right? Okay, let's move on to the next question. As the altitude of the aircraft increases, what happens to the air pressure? Not the atmospheric density, or rather, when the density altitude increases, the atmospheric density decreases. So if we want to maintain the same angle of attack and also keep level flight at a higher altitude, then what should we do? What should we do? What should we do? We should increase the speed, right? The speed that increases is true airspeed, right? Okay, when the true airspeed increases, what should the corresponding indicated airspeed be like at this time? What should the corresponding expression be at this moment? Why doesn't it change? I'll ask the student at the very back over there. The plane maintains level flight. Maintains level flight at a high altitude, and then, if the angle of attack remains unchanged, what should its true airspeed be at this moment? Can the student in front of you tell you? The plane maintains a constant angle of attack, transitioning from level flight at a lower altitude to level flight at a higher altitude. So what should the airspeed of the plane be at this moment? Yes, right. Transitioning from level flight at a lower altitude to level flight at a higher altitude while ensuring the angle of attack and lift coefficient remain unchanged. What should the airspeed be? What kind of airspeed is this increased airspeed? True airspeed, indicated airspeed. True airspeed, right? Then what should the indicated airspeed be? Does the indicated airspeed change at all? Why doesn't the indicated airspeed change? It remains even more constant. Come over here. That's not quite accurate. Why doesn't the indicated airspeed change? We maintain the lift coefficient for level flight unchanged, right? In this case, our wing area remains unchanged, so the dynamic pressure remains constant, correct? Then how do we calculate the indicated airspeed if we ignore various errors? We should divide the dynamic pressure by 1, 2, and then take the square root, right? And pay attention to which density we are using here. But its force will still appear. The student in the middle of the second to last row, near the door, please answer the question. Which word ru do we use when we are asking for an expression? Which state is it again? What should the number be like? Please sit down. These are basic concepts. If these fundamental concepts have not been memorized by today, students must review the previous material repeatedly after class. Otherwise, if this part is not mastered, it will be very difficult later on. In this context, we use a constant for our calculations, right? It should be 1.2235 kilograms per cubic meter, right? It is used under standard sea level conditions. Therefore, since this U is constant, as long as the dynamic pressure remains unchanged, the result we calculate should also remain unchanged. Okay, let's move on to the next one. When an aircraft is flying at a constant altitude, if the speed of the aircraft is reduced to half of its original speed, and in order to maintain level flight, what should happen to the angle of attack? What should the impact be? What should happen to the angle of attack? It should increase a bit, right? Yes. And then, what about the lift coefficient? The lift coefficient increases fourfold. Does the angle of attack increase fourfold? No, not necessarily, right? Because the lift coefficient is not necessarily 0 when the angle of attack is 0, right? Okay, so the above are the answers to this series of questions. This series is actually directly related to the basic relationship of our aircraft's level flight. If you couldn't think of the answers when asked earlier, make sure to review this part repeatedly after class. Then, returning from this question to our actual flight, let's observe what the situation should be like in actual flight. Now, when the aircraft is flying at a small angle of attack, at this time, let's take a look. A small angle of attack usually corresponds to a situation where the aircraft is at a relatively high speed, right? Yeah. Now, if we consider the angle of attack for the entire aircraft, we can approximate it as the angle between the aircraft's axis and the horizon, correct? It's this angle. When we are in normal level flight, we usually observe the horizon, or the distance between the horizon line and our glare shield. So, during normal level flight, generally speaking, if your sitting posture is correct, there should be a distance of about 2 fingers. This means the glare shield is about 2 fingers width below the horizon line. Normal level flight. All right, let me ask everyone, if the plane continues to slow down further, then if the impact increases, what should you be seeing? So, what we said yesterday is very correct, right? The angle of attack increases, correct? It's equivalent to the horizon's position not changing, but your entire plane tilts up, so the position of your glare shield will appear higher. when it changes to a large angle of attack flight with a relatively sharp angle, we will notice that your glare shield might be level with the horizon, or even the glare shield might block the horizon. At this time, for us pilots who are just beginning to practice large angle of attack flights, it will be a rather uncomfortable state because you can't see ahead. This is a physiological discomfort that needs to be gradually adapted to and overcome during the flight process. When our aircraft is flying, in fact, for small aircraft and general aviation aircraft, we cannot directly know the angle of attack. However, if we are flying level, at this time, we can approximately determine the state of the aircraft based on the relationship between the horizon and the sunshade. This serves as an important reference for us to determine whether we are safe during the flight process. All right, well, regarding the principle of lift generation in reverse flight, we have covered the principle of lift generation in this context. Next, let's talk about drag. So besides the main force, let's talk about the characteristics of the epidemic example. Slide. Let's take a look. First, how is the main force generated for two-dimensional drag? Its drag entirely comes from the boundary layer. Let's first see what a boundary layer is.
Moving the calendar to 15 velocity will give a better view of the ambulance growth.
Here we can see that by generating a bubble surface, and then as this bubble surface flows over a flat plate, we notice that the bubble surface moves backward. How is it? The speed is different, isn't it? Before reaching the flat plate, it pushes forward at the same speed. But once it reaches the flat plate, the part close to the plate, the closest part, no longer pushes forward, right? Then, as it gets further away from the flat plate, its speed continuously increases. In this scenario, as it moves perpendicular to the surface of the object, or in more academic terms, what we call the boundary layer, the flow in this direction, as it gets further away, the speed increases. This layer of flow is what we refer to as the boundary layer, or in the past, it was called the negative layer. In English, the term used is boundary layer. Due to the presence of the boundary layer, the corresponding two-dimensional drag on the aircraft is generated, as this boundary layer flows from front to back. When it first reaches the flat plate, the boundary layer is relatively thin. As it moves further back, it becomes thicker and thicker, which we can understand quite easily. The speed is zero at the point closest to the surface, due to the viscous force of the air, right? We refer to this as kinematic viscosity. The areas with lower speed pull on the areas with higher speed. And as this pulling continues, the low speed region keeps expanding. This means that as the flow moves from upstream to downstream, the boundary layer will continue to thicken. As it thickens, the innermost layer is actually attached to the surface of the aircraft or an object. In this way, a mutual pulling force is formed between the flow and the object's surface. This mutual pulling force is essentially the frictional drag of the aircraft. It is caused by the velocity difference within the boundary layer flow at varying distances from the object's surface, resulting in mutual pulling between the fluid layers, which creates this frictional drag. This is the first type of drag on an airplane that we want to introduce today, which is frictional drag. Let's take a look. The boundary layer itself is not actually in a very stable state and is subject to certain changes. These changes are influenced by some factors. Let's first examine the general physical form of these changes.
And those days and transition of non-layers from a lambda 1, 2 is 30-something on it.
We can see that at the very beginning, this section of flow has a boundary layer that appears to be very orderly, right? We call this boundary layer a laminar boundary layer, similar to the flow form we saw at the very start. On the innermost side, the speed is the lowest, okay? And on the outermost side, the speed increases. Moreover, this is basically a situation similar to an exponential change. We call this type of boundary layer a laminar boundary layer, and it is present here. Then, as the flow progresses backward, we find that it turns into a continuous flow, but it starts to rotate, right? it appears very chaotic, right? Similar to this segment, this type of boundary layer we call a turbulent boundary layer. Now, the turbulent boundary layer, although it still flows along the surface of the object, contains a large number of vortices inside. Now, the process when the boundary layer transitions from a laminar boundary layer to a turbulent boundary layer, we refer to this process as transition. Using the word transition, the laminar boundary layer is called laminar flow, and the turbulent boundary layer we call it. So, in relation to the actual flight of our aircraft, what is the significance of the transition from a laminar boundary layer to a turbulent boundary layer? Child, the first significance is from the perspective of boundary layer frictional resistance. The laminar boundary layer has relatively low frictional resistance, while the turbulent boundary layer has relatively high frictional resistance. How do we understand this? For example, it's like when we are squeezing into the subway. Bab, if everyone lines up and moves forward in an orderly manner, in this situation, isn't it because of the orderliness that everyone can relatively move forward quickly? However, if there are people cutting in line and causing chaos, doesn't it result in no one being able to move forward? This situation leads to the queue being unable to progress. And similarly, the frictional resistance increases. All right, let's take a short break.